In this tutorial, we will show how to perform a power spectral density analysis with SAP 2000. The model is a 50-foot tall pole meshed in 5 equal segments with a random forcing function applied at the 30-foot elevation. The forcing function is a power spectral density curve with a magnitude of 300 pounds squared per hertz over the frequency range 0 to 5 hertz. The goal of the analysis is to be able to plot the spectral density curves of the results, as the square root of the area under these curves will give us the RMS values that are needed for checking and design. Start by selecting the File New Model command and set the units to pound inches. Click on the Grid Only option. We will lay out a grid with 2 grids in each of the X, Y, and Z directions. The spacing in the Z direction will be 50 feet or 600 inches. We will set the left view to an elevation. Next, we define the steel material property of the pole. We will add a new material called pole steel. The weight density will be 0.28 pounds per cubic inch, and the mass will be calculated from this weight. The modulus of elasticity is 30 million psi. Now we will define the properties of the pole section. We use a general section. Our section will have an area of 10 square inches and a moment of inertia of 200 inches to the fourth. Shear areas will also be 10 inches square, and we can skip the other variables as they are not pertinent to our model. We will call this section pole and make sure that the material is set to pole steel. You can ignore the depth and width dimensions as they are for display purposes only. Now we can draw the pole. We will draw it in one segment, top to bottom. Leave the draw mode and select the pole and use the Edit, Divide Frames command to break it up into 5 segments, each 10 feet long. The base is fixed, so select the bottom joint and assign a fixed restraint. Make the nodes visible on our elevation view. And shut off the grids in both of our views. A check of the load cases shows that the program currently has 2 defined. We may delete the dead load case as we will be doing a dynamic analysis only. Select the modal case and click on the Modify Show button. Change the maximum number of modes to 3 and click OK. For this example, we will do only a planar analysis in the XZ plane. We are now ready to run the modal analysis. It is important to note that we are running a modal analysis only at this time. We are not doing a power spectral density analysis, as we require frequency information from our model prior to plotting spectral density curves. With the analysis complete, we need to determine what frequencies fall under our 5 Hz cutoff on the random forcing function. Our period and frequency table shows us that just one out of the 3 modes at 1.388 Hz occurs below 5 Hz cutoff. Next, unlock the model so that we may define the items needed to do a power spectral density analysis. Start by replacing the dead load pattern with a PSD pattern. Select the joint at the 30-foot or 360-inch elevation point and assign a unit load in the X direction. Now, go to the Define, Functions, Power Spectral Density command, and add a new user function. For our analysis, the value will be 300 from 0 to 5 Hz. Note, the coordinates are displayed in the lower right-hand corner. The last item to define is a PSD load case. We will add a new case called PSD. Make sure that the load case type is set to power spectral density. Under the loads applied, note that we will be applying the PSD forcing function as a load, using the previously defined PSD curve applied to the PSD load pattern, which is the unit load in the X direction. The scale factor is often useful to control the combination of forcing functions when you have more than one source. One of the most critical steps in the data definition process is setting the frequency. This controls the shape of the output spectral density curves and thus ultimately the RMS values. We will start with a basic selection of whole number values of 0 through 5, but will need to add significantly more points, especially around the frequency of the model. We will use the Add Modal Frequencies option. Here we tell the program to deviate from the modal frequencies by the specified percentage. We start with 0.1% to both sides, followed by 0.2%, and keep adding to the table, finishing with plus and minus 10%. it is important to have an adequate number of points around the structure's frequency. The last item to input on this form is the damping, which we will set to 0.04. We are now ready to run the analysis for the power spectral density load case. Once the analysis is complete, select the joint where the forcing function is located and go to the Display Show Plot Functions command. Here, we will plot the spectral density curve for displacement in the x direction. Confirm that the joint 4 function is the x displacement. Select the joint 4 function as the vertical function and note that the program knows to plot the values against frequency due to it being a PSD analysis. Note how narrow the curve is and why it was important to include numerous points around the fundamental frequency. What we are ultimately interested in is the square root of the area under the curve, which gives us the RMS value of the displacement. We can get this value by asking the program to display the deformed shape. A right-click on the joint shows that the RMS displacement value is 0.34 inches. A right-click on the top joint gives an RMS displacement of 0.74 inches. We can obtain the RMS values for the forces in the model by going to the Display Show Forces command and selecting the PSD load case. Right-clicking on the bottom member displays the force diagrams, and in this case, the maximum RMS moment at the base is approximately 43,000 pound-inches. This concludes this tutorial.